I think the main thing for me is it goes back to why I chose Julia, the package ecosystem, especially for developers of package to put things online and retrieve things. That's number one by a long shot. Number two will be this mix of multiple dispatch and randomly finding something new and seeing that it works with your package. And
Yeah.
number three is gonna be speed. Being a fast language is essential.
In this podcast, Abel discusses his transition from academia in Brazil to becoming a research software engineer in the Netherlands. He emphasizes his reasons for choosing Julia, such as its package ecosystem and speed. Abel details his involvement with the Netherlands eScience Center, where he collaborates with researchers to develop software solutions. He also covers his background in applied mathematics and his early adoption and advocacy of Julia. The conversation touches on Julia's smooth optimizers, its utility in optimizing nonlinear problems, and the importance of benchmarking for solver development. Abel shares insights into maintaining multiple, interdependent packages in the Julia and underscores the role of automation in testing and documentation. He also mentions his contributions to the Julia community through YouTube and expresses openness to collaborating and supporting both academic and industrial projects involving Julia. Welcome to Inspiring Computing. This podcast is where computing meets the real world. Inspiring Computing aims to trigger your curiosity by talking to proficient and advanced MATLAB, Python, and Julia users who use these tools to deepen their understanding of the world around them by simulating it, exploring trade-offs, and gaining insights that help their companies add more value. In addition to proficient users, we will be talking to product marketing, toolbox authors, package developers, and library maintainers to see what drives their development and what issues they're solving for others to benefit from. Welcome, Abel, to Inspiring Computing. I actually saw you talk at a Julia meetup here in Eindhoven, and I was triggered by Julia and how you maintain Julia's smooth optimizers. But before we get into that, maybe you can tell us who you are, Abel, and what do you actually do in your day job?
Hi, Gareth. Thanks for having me. I'm a research software engineer at the Netherlands eScience Center. My day job is essentially writing software, talking to researchers in the Netherlands, and figuring out their needs and writing software that makes essentially taking the long plan for research software.
And this is for the Netherlands eScience Center, according to your LinkedIn profile, correct?
Yes, exactly. Yeah.
So for those of us who do not live in the Netherlands, what is this?
The Netherlands eScience Center is essentially funding from NVO, or Dutch organizations, and we provide funding for researchers. But the funding that we provide for researchers is in the form of people hours. I get paid a normal salary, I work 40 hours, and the researcher applies for some of my time to work with him. So they say, hey, I need somebody to implement a machine learning model for this specific need, and they are granted like 9 months of research software engineer hours. So essentially, we work in a variety of fields. It can be very performance heavy, like improving C++ code, or it can be very domain oriented, implementing a machine learning model, which is simple, but for a specific usage. So we have calls throughout the years, and any researchers in the Netherlands can apply.
Do you primarily use Julia as a programming language, or is it depending on who hires you?
Yeah, it depends heavily on who hires us. Our main languages are Python, C++. You see a little bit of Tran. Some people try to use Java. Java I see a lot actually.
Okay. And so you're living in the Netherlands, but you clearly don't have a Dutch name. So tell me a little bit about what's your superhero story and how did you end up in the Netherlands in this eScience community helping researchers?
Absolutely. So I'm Brazilian, all todos. I have a bachelor's in applied mathematics from the State University of Campinas. And after that, I had a PhD in applied mathematics, emphasis in optimization. And then I became a professor in Brazil. Since 2014, I was a professor working with optimization, but I realized at some point that coding much more than I liked the other aspects of academia. And so I started to look for other things. And eventually I landed on the Netherlands, which has a large gathering of research software engineers or jobs like that. So that's essentially how I came here. I moved here in 2021.
Ah, okay. And then just out of curiosity, when you were in Brazil, were you teaching Julia? Were you one of the early adopters of Julia?
Yes, I definitely was one of the early adopters. So I started using Julia in 2014. The reason I use Julia, I think it's important to mention here. I started programming in C because of applied mathematics degree. The program you have C, and MATLAB was also very pervasive. I like both of those things. I still like those languages. They are very useful. And because it's an applied mathematics program, you use MATLAB a lot. So most of the classes had some kind of project in MATLAB. The issue is when you actually go to research, at least in my field, what happened a lot was that during a master or during a scientific initiation, you will have a code in MATLAB, and then it will not be performant enough. And then you will have to move to C++ or Fortran to do the heavy lifting. So I decided in 2009 to use C++ for my PhD direct. Since I'm going to have to move from MATLAB to C++ eventually, let's just do it in C++. And it was not a great experience because C++ it has too many pitfalls and it's too slow to be productive in that language, especially if you're starting in it. So in 2014, when I finished my PhD, I moved to my university as a professor, and I decided that I needed to find something else that was ideally a higher level than C++. Also, I don't want to lose performance. And I looked into Python a little bit. I looked into Octave. MATLAB was also being considered, but one of the main issues with MATLAB for us in Brazil is that it's an expensive software. So if your university does not have a contract with math, you have to get a separate funding to pay for that, and your students can't use it. And so I was trying to avoid the proprietary software because of that. Somebody told me about Julia. It seems like an interesting language, and it has some connection to Fortran, which was an integral part of what I had to do in my research. I was like, okay, I'm going to test it eventually. And eventually came in the late 2014, and it was amazing. Essentially, was like, it does everything that I need. How does this exist, right? So again, I'm from the mathematical background, so not computer science. When I say the language is amazing, I'm not looking to, it compiles, the compiler is, I don't know. I don't care about those things. I care about the math is done in a way that I can understand. I can use the linear algebra facilities, but also I can integrate with the other code that I had to work on, which was low-level Fortran code from 20 years ago, right? Essentially, that mixture, which eventually I learned is called the two-language problem.
So you were doing your PhD in Brazil, right? What was it about? This is about optimization, but can you be a bit more specific about it?
Yes. So this PhD was about taking an existing optimization method. It worked for a specific class of problems. So originally, the method was only working for equality constraints, and I was going to make it work with inequality constraints as well. The code was originally written in Fortran, and the programming part of my PhD was to take that code and make the extended version work in C++.
Oh, I see. So that's where you begin with the headaches of C++. And
Well, yeah.
the learning curve is not so easy if you're not with a computer science background. There's a whole wide variety of concepts that get thrown at you.
So yeah, one thing that I notice a lot is like people use Fortran and C for this. And when they say, I'm using C++, unless you actually came from a computer science background and a lot of C++, mostly is C with classes.
Yeah.
It's no STL, no auto point, nothing. It's just C with classes.
Yeah.
And that's an interesting thing to look at.
And then you discovered Julia, and then you said it had everything you needed. Were you teaching with Julia or also doing your research at Julia? Is that kind of where it got started?
Yeah, exactly. So I needed to teach, and so I do not want to put my students through the burden of having to either buy MATLAB or depend on the university lab. It was an alternative for them, but it was too slow. And I also wanted to do my research, which meant I want to do something fast, but I want to prototype quickly. So essentially, every language that I considered had some kind of issue in those things that I wanted. So I use Julia for my teaching. I taught initially numerical methods in Julia,
Okay.
ordinary differential equations, those kinds of things, like basic of learning a mathematical programming language, nonlinear optimization from the very basic. Okay, let's do everything in Julia. And that, of course, combined with my research was doubly nice.
Nice. And then, so you started teaching university students, I'm guessing around third year, fourth year students, which are getting used to programming, or is it maybe a bit earlier in Brazil?
It's even earlier, yeah, like second years.
So second year, and this is probably one of their first or second programming courses, and they're applying theory and computational thinking. So how was that journey? Was that a difficult thing for people to pick up, or is it the professor gives it to you, bunch of smart people, it doesn't really matter which language, you're going to pass the course and you pick it up?
A little bit of both. So they usually had C before, and I had the transition, which they moved to having Python. So they learned to code in either Python or C, mostly C in my days, because I'm not that old. So they already knew a little bit of what to expect. And those people navigated Julia easily because they knew the basics of programming logic. Well, of course, it was easier for them. But yeah, also, I think the most challenging part of teaching with Julia was like they expected an IDE that they just clicked and it ran. Eventually, I took over the labs and they were Linux as well, so it was easy. and their personal computer were always Windows. So I had to think of this has to work for them and for me as well. And the very, very beginning was like, I just want to have something that they can run easily, but also that I can grade. So I want ideally to use Git for the assignments, but they also just want to click and send me an email. The harder part was actually the best practices.
Because this is before Pluto arrived,
This
right?
was before Pluto, yeah.
So Pluto, I think, changed the game there a little bit.
Yeah, I had to improvise a lot.
So the other thing that you're really well known for is the Julia Smooth Optimizer. So how does this fall into the story? So you were teaching, you're doing research, and then woof, you decided to create Julia Smooth Optimizers. How did that happen?
It was a little bit magical like that. A little bit of the basics of how a nonlinear optimization developer works. This is my days. Okay, I'm not sure exactly how they are doing it now, since I've been away for a while. But in those days, we learned how to do things. It was you prototype something in MATLAB. That's essentially you have a mathematical theory that you prove that it works, or is almost proved that it works. And then you prototype. Strangely, you prototype only after you know that the theory works, but that's another issue. Then you did some basic tests, and I'm going to get 5 problems that the paper describes. These are like 2 variables, 3 variables. If that works and you actually want to publish your paper, your software, and say, this is something, the theory is sound and the software is competitive, you're going to have to do some actual benchmarking. And the actual benchmarking is you're going to take a Fortran package and you're going to take your software, you're going to link those two, and you're going to run the benchmark on your problems. And the reason is that an optimization problem is very hard to describe because you want the derivatives, the first, second derivatives of a lot of things. So to describe an optimization problem in a way that is efficient to compute the derivatives, you need something very powerful.
Yes. So maybe to take a step back, right?
Yeah.
Can you explain at a very high level what that means to you and maybe a few of the classes that you're thinking about when you say the word optimization problem?
Great. So when we say optimization, mathematical programming, essentially, and what it means is essentially you have a set of possibilities. Let's say you want to build chairs and tables, and you have a given amount of materials, so you can decide whether you want to build 15 tables or 40 chairs. You have a demand, for instance, so you need to deliver at least 2 tables and 7 chairs or something like that. You have constraints, which are the demand has to be satisfied, the materials available, etc. And you have an objective, we call it the objective function, which is essentially you want to maximize your profit or minimize waste or anything like that. So if you can describe your problem in a mathematical formula, you have tools to help you do that. And your problem is something like, I want to minimize or maximize something under constraints. That's essentially an optimization problem. or a mathematical programming problem.
So maybe just to be clear here, there's a difference in solving it by pen and paper with equations and asking a computer to solve it, right? This is a fundamental difference that sometimes people get confused about. Can you explain that a little bit?
Yeah, essentially, when you're actually doing these problems in real life, those are completely untreatable by pen and paper. So it's like a machine learning model. So when you say, hey, let's learn about classification, you plot in a paper, you say, hey, this is my x-axis, this is my y-axis, here are some dots. You draw a line and it's classified. Everything from one side is red, everything on the other side is blue.
Yeah.
Okay, let's do the same now for an actual problem. And then you have something completely unreasonable. You cannot see it. It has 20 variables. It has, I don't know, 1,000,000 data points. The number of possible solutions is unbearable. But yeah, essentially you have too many options to consider them by hand. So you have the brute force approach, which will be, let's try all of the possible solutions and see which one maximizes my profit. That becomes putable. So you will have to wait for years and years for a decent solution.
So for me, I remember when I was in university, I had this magical moment where I always thought that maths had to be solved analytically, right? So given any problem, I could solve it, right? And you learn linear algebra, you're solving multiple equations at the same time. There was always a way to get there. And okay, you add bigger or smaller matrices and then maybe more integrals, more derivatives, but you could actually calculate things, right? And then when I first started programming with the computer, I always tried to reproduce that. I was surprised the first time one of my professors said, sometimes you can also do it iteratively. And I said, what do you mean iteratively? We either know or we don't know. And he described it to me as some problems are better suited to iteratively get there by saying, okay, I'm going to take a slight step in this direction. And then if I keep doing this, eventually I will come to a solution, and it might not be the best one, but it's a solution that is valid. And I had never thought of that because I always thought the maths was analytical. And then this opened up the whole horizon of, oh, this is what computation is about. Optimizing problems changed for me because you can take pretty much any linear problem and write down the equations and you can get the answer. And okay, maybe if you're better at maths, you get there quicker. Okay, you could also do that in Julia or Python, but then the real world hits you. Some of these equations are not just linear. This is not just an x plus y plus z. It doesn't matter if you've got 20 variables. The example of the chair and the table, that's easy-ish, I would say. But what is not so easy is when you start saying the speed of which a table is actually made or manufactured and the waiting time and the constraints of how much wood is wasted and what is a better way of doing it and waiting times of delivery services and things like that. When you start all putting this together, it feels like mathematically, I don't want to look at this equation and I don't want to do it symbolically. I want to do it numerically, right? And this is what you're talking about when you say optimization problems. Is that it?
Yeah, exactly. It becomes harder for some classes, especially the ones that I talked about, the nonlinear kind. Sometimes it can't mathematically have an explicit solution. So you really have to iterate to have something good enough. It's like when you learn a linear regression and then you learn, oh, this is interesting. It's easy. I can do it by hand. And then you learn logistic regression and you say, oh, actually, I cannot do it by hand. This is a bit more complicated because it's a line and it's a hyperplane separating, etc. But actually you have some untreatable values. It's like a neural network. So you get the harder part, which is you can't even visualize what's going on, even in the simplest example. It has too many variables. And actually training a neural network is an optimization problem because you're essentially minimizing loss or maximizing the fit of your model. That's the kind of problem that we are talking about. For instance, you take pictures from the Colosseum with a machine and you have essentially just 2D pictures, the direction that the camera was pointing and the GPS of the robot. So you have a lot of uncertainty because the GPS is not perfect. And you have a lot of depth guessing because they essentially only have a 2D picture. So it's a highly nonlinear problem. It's very interesting, very hard to solve. So it's very interesting, this kind of problems. Highly nonlinear, that's optimization.
Right. When you say nonlinear, right, mathematicians, they tend to use this jargon very loosely and it's very clear to them what it means. But what does that mean? If you have an equation, if it's like just x and y that's linear, right? But if you say x squared, square root, the exponential, the derivative, the integral, or the triple integral, things changing over time, that is what you're meaning by nonlinear, right?
Yeah, so nonlinear can mean anything from just polynomial to exponential to actually having integrals in your constraints. You have subclasses of problems, which are like ones that you can obtain analytic, which are the nicer ones. Some are even non-differentiable, which are, I think this is probably one of the most current fields of study right now. This kind of non-smooth optimization adds another degree of complexity, which is you can't even compute the derivatives to see that if you're actually going the right way.
So if I understand you correctly, that this nonlinear term, it actually means that there's multiple mathematical approaches in solving different categories of problems, right? So depending on how these equations are described, that lends itself to different categories of problems, different categories of solutions, some possible analytically, the vast majority not. And then there's actually different algorithms that then are used to solve these problems.
Yeah.
Is that how your Julia smooth optimizers appeared? Because the world is super confusing. Tell me how you got there.
So these problems are hard enough that you don't have a unique way of solving it. So even the most basic ones, if you look into scikit-learn for logistic regression, you have one of the arguments is the solver that you're going to use. Something like LBFGS or trunk. I don't remember the name that they use. But essentially, it's a very simple problem, logistic regression, from an optimization point of view. It is nonlinear, but it's simple. And even then, you already have different ways of solving it. So like I want to use only the first derivative, or I don't want to use any derivatives. So you have a lot of ways of implementing solvers. And you also have new theory being developed that says, hey, I realize that we can actually do this new thing that's going to make our solver faster, but it could also be more expensive. These old fields are not so much, but in more specific fields like machine learning, you have new methods being developed as well. So because of that, you have to benchmark your optimization solvers one another, and also with the classic ones, the ones that people still use and they have some fame.
So what is actually Julia smooth optimizers?
Yeah, great. The idea behind Julia smooth optimizers came because of this benchmarking. So you have to benchmark the solvers, and the way that you had to do it and still have to do it is find a collection of optimization problems implemented some way. So finding derivatives of a generic problem is not easy. And there is this package called qtest. This is a Fortran package. This is the third iteration of a package. So it exists since the 1980s. And it's a Fortran package that you have to use. How do I use a higher level language with this Fortran package? I have to hope that the developers are supporting Python and MATLAB. Well, but actually, if I'm using Julia and you actually can access things directly, maybe I can use Julia and just call the functions that are implemented in qtest. Essentially, that's what I did the late 2000. So I investigated how can I use this benchmarking package, which is written in Fortran directly from Julia. I did that, a simple test, put things online on my GitHub, and the developer of the qtest package, the original one in Fortran, said, hey, I'm doing the exact same thing. Let's work together. So that's how for Julia smooth optimizers began.
Interesting.
Just putting things online and the developer finding and say, let's actually work together so we don't waste resources.
So I didn't realize that Julia smooth optimizers started with a history of benchmarking. I always looked at it, maybe I'm newer to the game, as a collection of tools written in Julia that enable people to solve nonlinear problems. And instead of Googling left, right, and center to say which package is the best one for this type of problem, which often is hard to describe and you rely on different sources, which may or may not be reliable. I always thought that Julia smooth optimizers is that one-stop shop for anyone who wants to solve an optimization problem within Julia ecosystem. Is that a fair assessment of what it is today?
It is what we hope it becomes. Again, we have other very big optimization organizations in Julia, and now we are doing a lot of that. But I think probably the biggest one in that sense is the Jump organization. It was never our main intent to compete, and we are definitely not competing. And that's one important thing to say. We are not competing with Jump. So our main idea, like our main goal, even today, we want to enable streamline development of optimization solvers of the nonlinear kind. The nonlinear optimization solver development requires some things that the linear optimization doesn't require. That was our main goal, was developing the benchmark. And now we have benchmark. Let's write a way to show the benchmarks in a nicer way. Now we have that. Let's write something else. And eventually became what it is now, which is over 50 packages. So it was not our main objective to provide the end user with an optimization solver. Now we do have that, and we are working on things to make it even better. We are working on something that is going to be essentially the main entry point for optimization in general of the nonlinear kind.
Okay, so then this Julia Smooth Optimizers is your primarily audience was actually not the end users, but it was developers, right? So people who were doing fundamental research, and you found that there was this niche where people were struggling with the software building, testing, documenting skills, helping people out, and said, okay, we've done this for project A, we've done it for project B, we might as well take the same approach. And then if you take the same approach enough, then you become a bit more streamlined. But I'm assuming you also then started participating in all of these projects, digging a little bit deeper in. But then how do you maintain all of this? This feels like a difficult challenge that maybe people don't perceive. Tell me a little bit more about that.
Yeah, it is the main challenge right now, is maintaining everything, keeping everything up to date. That's one of the great things about Julia. First of all, I cannot stress this enough. When I started, we did not have many of the things that we have today. So if you look at our older packages and you actually look at the commit history, you're going to see a lot of the scars, right? The battle scars. But Julia helped a lot in many things. One of them being this expectation of you're going to have good documentation, a license, a CI pipeline for your packages. So because of that being in place, it made our life a lot easier. But still, we have a lot of issues in maintaining these things. So one of our main complications right now is not breaking our dependencies. As I said, you have this benchmarking package. This benchmark is one of 10 other possible ways of obtaining an optimization problem. Whenever I make one update in the core model, I have to update all of those things. So one of the things that I have been looking at for a while is how to make this a bit more streamlined as well. So how do I keep my dependencies updated?
So maybe to help you out here, you have these 50 packages, right? Yeah. So you say that 50 packages, then they're not independent from each other. So package A depends on package B, which depends on package C. And they're all potentially developed, maintained by slightly different group of people. This problem is actually quite common, I would say, in pretty much every large software organization, right?
Yeah.
And Julia is also, doesn't mean that if you use language A or B, this problem disappears. But I think what you're calling out and is interesting, what I found interesting when I heard you talk in Eindhoven was how you dealt with the dependencies and how you did the testing in Julia and how ultimately you've automated as much as you can. And I think that's where large software teams iterate towards. So can you maybe tell me a little bit about some of the tools or the iterations in these automation that you've done in the past?
So essentially what we did for solving these dependencies problems is automation. That's one of our main objectives, is to have a quick feedback of things are breaking. So there's this thing called downstream testing, which is essentially, instead of you testing when a new dependency of your package comes along, you test the dependence of your package. So in our main core package, which is NLP models, I have a CI pipeline. So a CI is one of the GitHub workflow files, essentially, that runs every time I make a new pull request. It's going to take every one of those dependencies, which are about 20, and it's going to run the new pull request on those dependencies. I'm not just testing my package. I'm not testing only my manually written tests. I'm also testing the tests of other packages. So this is not new itself, and I'm not doing anything magical. I think that just this is also not trivially available. So we had to do some bash
Right.
scripting there.
So then maybe to understand a little bit, in the Julia ecosystem, right? I
Yeah.
think it is encouraged, if I understand correctly,
Yeah.
that you create small packages, right? So maybe in other ecosystems, maybe like in a C++, you tend to make things a little
Yeah.
bit bigger in a big bucket, and then you contain the problem as much as you can. I think the best practice in Julia is to split things up as much as possible. So you end up having, by definition, many more packages, which makes it slimmer, faster, better in many aspects.
Yeah.
But if they start depending on each other, that then for the maintainers, in this case, you, for Julia
Yes.
Smooth Optimizers, it gives you a bit more work, right?
Yeah, exactly. It is a trade-off that we had to make at some point. Originally, we had one big package. Problem with that is now you have a constraint on your big package, which is anytime that I want to make one small change, I have to update a lot of dependencies, internal dependencies of that package, because they are so intertwined. So yeah, Julia has that. And I think that's a very nice way of dealing with things, which is writing smaller packages and having a longer line of dependency is good. It's not actually that hard to have something like downstream testing, but it does involve some workflow hacking.
So maybe just to understand, which are the more common packages that you're inside Julia Smooth Optimizers?
Yeah, the main packages that we have are linear operators, and the packages that linear operators is mostly attached to is Krylov. So Krylov methods are methods like the conjugate gradient method. So that kind of iterative solving of either linear least squares or linear systems. And linear operators is a way to avoid computing, having the explicit matrix. So this is like a lazy operator, lazy matrix, I guess you can say.
What are a few other packages that you are maintaining, supporting?
There are two other packages that also go together that we like a lot. Is Percival. This is an implementation of an older paper. People probably don't want to know about the details, but it's an augmented Lagrangian method. This solver is pure Julia. It has some competitiveness for pure Julia solver. And we also have the AB models, which is a way to create optimization models using automatic differentiation. Using those two, that's going to be one of the main ways to solve an optimization problem very easily. So you can, in a few lines, just write a problem and send to Percival, get a solution. You can have something 5 lines of code. So those two combines are going to be one of our ways of dealing with the end user.
So I'm looking at the GitHub page at the moment.
Yeah.
I see indeed that you've categorized Julia Smooth Optimizers into linear algebra, linear and quadratic optimization problems, nonlinear least squares, and general nonlinear optimization. Each of these have got specific Julia packages. But then just to make sure I understand correctly, does this mean that I choose package A and I can then reuse it in package B and compare and benchmark it for the same category of problems? Is that the kind of main driver? And you've helping people say, okay, you've done in problem A, you want to benchmark the same thing with packages A, B, and C. This makes it possible. Is that how you strive to make this a reality?
Yes, that's one of the main uses for our developers. We have 2 main user groups. For the developers of optimization user group, this is one of the main driving forces. You can obtain problems like when you want benchmarking or you want to solve an industry problem. So you have the input stream, you have then your optimization solver, and then you want to just visualize the results. We are developers. I'm not a professor anymore, so I don't have students working on this. But my colleague, the co-creator of Julia Smooth Optimizers, he still has students, and their PhD involve creating the optimization solvers or creating extensions. And so we still want to enable that fast development.
Because the other part of it is Julia, the expressivity of it is very much associated for mathematical minded people, right? So I think it started off with a very mathematical background, and when you read Julia programs, it just speaks to mathematicians or people who are used to coming from that background. So I do indeed like the idea of making it easy for people to use that and develop it. But it's often the case that if you're going to develop a package, you don't have the software background and testing. You don't think about testing all the edge cases. So having an overarching team to help you with that, getting the testing, streamlining the documentation, the examples, That I think is a huge added value for anyone going down this path, right?
Exactly. We do hope that it is useful for the people in that sense. And people can always talk to us directly, uh, but always happy to find an extra hour to update something that you find.
Yeah.
We try to maintain our core packages.
So maybe just as another thing is my naive look on this is every time I've done a optimization problem, the vast majority of the time is actually defining the problem, right? So that
Yeah.
definition of the problem is super, super important. And actually you can define the same problem in multiple ways. And one way can actually be significantly faster for a computer to get the solution. Do you also express and teach and show people that? Or how do you deal with that?
Yeah, we try to be agnostic. That also touches other packages. So that's one of the things that we do not focus a lot,
Okay.
except for AD and LP models, which we are heavily invested in having something that is very user friendly, but also efficient. So like people will still find that working with Jump is one of the best ways to define an optimization problem, even after we have AD and LP model as nice as we would like. So writing something using a modeling language like Jump, and by the way, Jump is not part of Julia's Mod Optimizers, if that was not clear. It's very nice, but we don't want to only limit ourselves to Jump. So if you wrote something in Jump, we have a package called NLP Models Jump that converts your model to ours.
Right.
We also have something to convert AMPL models. So AMPL is essentially a modeling language. It's proprietary, so I'm not sure what they wrote in it, but it's not a Julia package. But we do have integration with AMPL as well. So we have integration for if you want to write explicit code for everything yourself, you don't want to trust any modeling language, we also accept that. Or if you want something a little bit more on top of existing things, like we have something called PDE and NLP models. So when you have an optimization problem with constraints that are actually partial differential equations. So this, it is complicated just to explain. To solve it is much more complicated. So we use all of that capability of Julia. We use existing packages, in this case, Grid App, to convert your Grid App PDE into our optimization problem in a way that makes sense for us and for you as a user wanting to optimize something.
So then that's a fundamental thing that you've done there, right? There's multiple ways to describe a problem, and then being able to switch between the definitions of these problems so that different packages can read and import them, and now enables you to do this benchmarking at a much faster and quicker pace, right? And that is actually historically a bottleneck for anybody in this domain. And maybe just then to understand a little bit more is these Julia packages, are they actually used outside academic workflow, or is it primarily for academic research? I have to believe you're collecting industrial usage by now.
Unfortunately, they are mostly used in academic backgrounds. So maybe people are using them inside some industry, but they haven't got in touch with us to say that. I would imagine that they are probably using Krylov or one of our wrappers, but maybe they are also using something very small in a concentrated problem.
Let's say I'm a PhD and I have a new solver that I want to implement. So I come to you, I say, hey, Abel, I have this new solver, I want to implement it. Tell me what happens from that moment that you find this PhD person with a new solver in Julia. How do you bring it into your ecosystem?
Yeah, very nice question. So let's say you want to write an optimization solver and you want to follow our guidelines, right? So let's say you want to write a JSO compliant solver. First thing to do, you go to jsotemplate.jl and you use that template, use the GitHub feature, use this template. Essentially, you have already a lot of the good things that we want, the project TOML, git ignore, some CI, etc. A lot of those good things, documentation. So this was created with package template.jl, okay? Not an alternative to package template. We are already using the good things that they have. In addition to that, we are adding some JSO things. Second thing is you just have to follow one or two tutorials to say, hey, what's the API to access the optimization, that objective function? What's the API for the gradient? That's it.
And then do you then become a maintainer of the GitHub? So I am a PhD student, I've got my GitHub page. How do you deal with that?
We do not take it from your hand. It is your work, and we will help you have it working, and probably going to find it useful. If you do not use it, you will have to find a way to implement the benchmark yourself. And that's about, 60 hours of your life.
So then, okay, so I'm this PhD student. I follow your guidelines. I create the package template. I tell you about it. Then do you start monitoring it and then start your testing and then add another package to it? And if there's an issue, do you generate automatic issues for me, or how does that work?
We can do that. It depends on your conversation with us, essentially. So we don't do anything automatic like that. But I would like to have my package part of this automatic testing, we say, sure, let's do that. And that's essentially one line in our configuration file.
Yeah.
And then if something breaks only on your package, we can create an issue or tag you on the pull request to see why it's breaking. So as long as you keep replying to our messages, which is, I think, the most important thing, we're going to communicate. As long as we are communicating, we can keep your package on our pipeline of testing.
Yeah. So then you're collecting this group of solvers that have been developed by lots of people. They're probably part of the PhD. Some of them stop being used. Some of them maybe take off and become more popular. And then you just keep this under one nice umbrella for people to what's out there and help compare their work. But maybe I'm curious now, how do you actually do your testing? So I think many people with a mathematical background, their concept of a test is maybe not the same as a computer scientist test. So tell me a little bit how your testing is actually done in Julia.
So two things. One is that we actually don't keep the external packages in our umbrella. Only your actual PhD or master's or even undergrad students are in our umbrella. Or if you actually want to be part of it, that's something else that we can talk about. But by default, we do not include anything else. Yeah. And so actually the tests, you have both kinds. We actually have some of the traditional computer science kind of tests, which are like, is the input being accepted without throwing error? So a bit of like unit tests or integration tests, that kind of thing. So we do test that with your package. We have something called a solver test.
Tell me more about the solver test.
Sure. So like a compliance solver is a solver that accepts a specific input and spits a specific output. So because of that compliance, we can actually write some things that are like expected to happen. So if I write a problem that is very simple and I expect the solution to be correct.
Oh, I see.
So it's a little bit like not only it works without throwing errors, but also it has the minimum expected efficiency.
But you write the solver test, so you have a layered approach, right? So you have your unit tests, then you have your solver tests, the way you referred to. And then what other tests do you have?
I think for a solver, those are it. Yeah, for the model, we have other things, yeah. But for the solver, we have that only.
And for the models, what does it look like for the models?
Yeah, the models, we also have some other things which are like, you have some specific things in Julia that can happen, like you want to pass a view of an array. So some kind of edge cases. So we test a little bit of those edge cases as well. Yeah. So one of the tests that we do, this is completely optional. And if this is a very specific use case, right? If you're a developer, not only of a solver, but of a model. So it's not your end user case. It's a more complicated use case, I would say. But also one of the nice ways of extending the optimization model. Like I said, the PDE constraint optimization is a new model. We also test multi-precision. So that's one of the things that sometimes people don't find that interesting, but for us, it's very important. If you're a classical developer, C++, you think 64 bits, 32 bits, but we are actually interested to see that the model works for float 16 and big float, right? So it's a kind of silly thing, maybe because these are slower. Yeah, but if it works for those kinds of things, so it makes it more likely to work for specific types, like working with CUDA arrays, right? So we cannot actually test with CUDA because we don't have a dedicated machine or because of funding.
So, because the other thing is, I think part of the beauty of Julia is it is actually quite easy to get it to run on GPUs.
Yeah.
Does your benchmarking, do you take that into account, or do you lock down your hardware with or without a GPU, say, okay, it's all relative on this specific hardware?
Yeah. For our solvers, we only test CPU and we only test with GitHub, and that's it.
Okay.
For Krylov, so Krylov is probably one of our most used packages. It is actually tested on GPU. There are benchmarks. I don't know if all of them are online, but Krylov is tested on GPU and should be working with GPU as well. It's one of the important things.
And when you look at helping people, do you also guide them through documentation? Do you have best practices of how to get your documentation up and running for others to jump on a project?
That's a great question. You're asking about our documentation or the documentation of their package?
Both. Okay.
We don't have a lot written down, so we do have some things, I guess, more internal. But one of the things that we do have is the template includes the basics of documentation. So if you have doc strings, they will be built and put online automatically. And they should complain if you don't have, your desk should complain that you don't have doc strings. So a bit of best practices is in there. This is actually one of my interests right now, is to write a doc string test, or at least find one. I don't have to write one. If you're writing one, just please send me an email so I can actually use it in Julia Smooth Optimize. We'd want something to check the format of documentation of the doc strings.
And then for yourself, on your end, how do you do your documentation? Do you have a large process around that?
Yeah, we have, for our documentation, we have the internal documentation, so using documenter.jl, API documentation, always hosted in the package. But we also have the website, juliesmoothoptimizers.github.io. You're going to find the tutorials for all packages there, at least the ones that we have written so far. And that's actually one of the things that I found very useful, is because we have so many packages and so many of them are like a very specific use case, instead of just keeping them all separated, we aggregate all of the documentation in a single place, all of the tutorials in a single place, and we build it.
What's the toolchain behind that?
We have a repository called JSO Tutorials. Essentially all tutorials will go there. And when you submit a new pull request, creating a tutorial or changing something, GitHub action trigger, but only for the specific tutorial. So that's essentially making it work in parallel, so I don't have to rebuild everything all the time. And there is one of the actions to deploy that to the website. The website currently uses franklin.jl, which is another Julia package. Again, Julia for everything, from web to optimization. But the tutorials themselves are using Weave. So it's an amazing combination of a lot of things.
I think that speaks to the power of the ecosystem, right? So the underlying language is very fast, but there is indeed more to Julia than just language itself. The power comes from the ecosystem. And many people don't perceive that web development, web pages can be built in Julia. So it's good that this is a good use case for it.
It is indeed. And hopefully we're going to find a student to do something with Jenny as well. So he has a even more attractive and interactive aspect to it.
If I was to ask you, what are your top 3 favorite things about Julia? What would you say they are?
Great. I think the main thing for me is, it goes back to why I chose Julia. One of the reasons I chose Julia in 2014-15. Like, I was in my lab during my PhD, the person to go to when installing the Qtest package, because it's like 45 minutes of doing a bunch of make files and selections and things like that in 3 different packages, right? That was one of the way that I got, for instance, beers as gifts from professors saying, thanks a lot for installing these. And now to install Qtest, the Julia version of Qtest, you just say add Qtest. That's it. It installs everything automatically. Amazing. The package system, especially for developers of package to put things online and retrieve things. That's number 1 by a long shot. And now number 2, it gets more complicated now. Number 2, let's see. Yeah, I think number 2 will be the of this mix of multiple dispatch and randomly finding something new and seeing that it works with your package. Like, I think when I first saw the interval, I forgot the full name, is interval arithmetic, the package that it creates a new number and magically works for this very specific use case. And you're like, whoa, this is amazing that somebody thought about this, right? And so this kind of expressiveness is amazing for me as well. And
Yeah.
number three is going to be speed. But yeah, like being a fast language is essential.
So I think it's also fair to say that it's a language that has evolved. It's a relatively recent language compared to
Yeah.
maybe Python, and it's still evolving. So are you aware of any cool, exciting things which are coming downstream in Julia language that you're excited about?
All of those things about time to first plot and not being easy to just ship the compiled version. So I think it's gonna improve a lot of the time to first plot, and I'm very excited about that. But I'm actually very hopeful for when we're gonna actually easily compile a binary in Julia. So I'm excited to see that happening. I think that's one of my most expected. Yeah.
Nice. And just out of curiosity, when you're programming Julia, do you have a preferred IDE now? So you said you're a Linux person.
Yeah.
Do you use VS Code now, or do you
VS
point
Code.
to Pluto, or what's your environment look like?
So I'm also a YouTuber, and what I do is I use Pluto to show whatever I'm doing in Julia. And I'm a YouTuber mainly focused in Julia and also about talking about life in the Netherlands, but that's for my Brazilian audience. I always use Pluto because it's nice to just change things and have the Pluto UI. That's amazing. For developing code myself, though, I always use VS Code. I was a Vim user, like a hardcore Vim user. I tried Atom, I tried whatever else was before, did not change. VS Code actually sold me.
So what does your VS Code environment look like? You probably customized it a little bit.
Actually, that's one of the things I like about VS Code. I don't customize it a lot. The basic stuff in there is already very helpful. I think I only install Julia. I install remote SSH for sometimes I want to work on other machines. The basic things like the multi-select are helpful. I still do most of my testing in the terminal, so I code, but I don't alt-enter to run the Julia code. When I'm just doing a little bit of testing, that's also one of the helpful things. So this is maybe a tip for the people. You can do kind of notebook environment without actually creating a notebook in VS Code with Julia. You just create a comment like a hashtag, and then you can alt-enter, and it just runs a cell of your code. So I think that's very helpful for just testing instead of booting up a Pluto or a Jupyter notebook.
So let me ask you a question there. So I noticed that you make YouTube videos left, right, and center. So tell me a little bit more about this. What's driving this?
Oh, so in 2019, 2020, something happened in the world. Let's not name it. And I was still a professor then, and we had to teach online classes. And it was the perfect chance to do something that I wanted to do, which was create YouTube videos about programming in general. So I gave my classes online, essentially putting them on YouTube and saying, hey, look at this, right? I did some live coding as well on Twitch. I still have a Twitch that's less active now, but those classes eventually became like videos in a playlist about numerical optimization in Julia, right? And I still do it, even though I'm not a professor anymore. I still do a lot of videos about Julia. Most of them are in Portuguese, but I decided recently to actually do videos in English. So I'm gonna be having a lot more videos about Julia. If you like Julia, please subscribe, youtube.com/Abel Cicada. Julia for specific usages, Julia for random things. Go ahead, look me up. And
so I can tell from this discussion that you're looking for volunteers and helping to contribute to Julia Smooth Optimizers. What would be the right way to reach out to you, and what would the reasons be to reach out to you?
If you're a researcher, a student, PhD student or not, or even more interesting in the industry, working with mathematical programming, you can reach out to find me at abs.cicada@gmail.com. We can talk about how Julia Smooth Optimizers can help you in your research. We can talk about whether I can give you some opinions on what you're doing. We can talk about consulting if that's also interesting for you. And if you want to help out with Julia Smooth Optimizers, you can go to our main organization. You can go to our repository, so github.com/Julia Smooth Optimizers /organization if you don't have any specific package. There's a discussion in GitHub that you can leave a comment, leave a question, or anything like that. If you have a specific package in mind, you can get in that package. We do have some Zulip, but it's not public. This is very technical thing, so it's not usually useful for users. But if you're a developer and want to get in touch, let us know. If you're interested in Julia in general and not specifically for optimization, I'm actually invested in finding a Julia meetup in the Amsterdam region. So if you're in the Amsterdam region and you want to meet up in person to talk about Julia, let me know. There are some colleagues at work as well interested. We are very excited about pushing Julia to the whole Netherlands.
This is a great place to stop this episode. I hope it triggered your curiosity in some shape or form of how MATLAB, Python, or Julia are actually used in the real world. If you did find it interesting, just subscribe in your favorite podcast player, and while you're at it, write a review, as this will help the podcast going strong. In addition to that, don't be shy, share it with a couple of friends, as who knows, one of them might be a future guest on Inspiring Computing. Thank you.